we've talked about work as the transfer of energy between the environment and a system. Either positive work, where the environment is adding energy to the system, or negative work, where forces in the environment are taking energy out of the system. However, in many situations, we are interested in how quickly the energy is transferred to or from the system. For example, the same amount of work is done against gravity to lift a ton of bricks up by 10 meters. Now, that work can be done one brick at a time, or it could be done by putting this ton of bricks on a pallet and lifting it up with a crane. In either situation, the total amount of work is the same. However, it would take much, much longer to take one brick at a time and carry it up a staircase, for example, to lift up that full ton of bricks, as opposed to using a crane to lift all of them quite quickly. So when we talk about this rate at which the energy is transferred, we're talking about power. Power is written as a capital P, and power is defined as the time derivative of the energy of the system. If this time derivative is positive, that means work is being done on the system. If this derivative is negative, it means the energy of the system is going down and the work is negative. Also to say this is the instantaneous power, the instantaneous energy being added to or taken from a system. What we'll also see, similarly to what we saw for velocity and acceleration, for example, is an average power, which is looking at the total change in energy of the system divided by the total time that that change in energy requires. In either case, the unit of power is the watt, named after James Watt, the inventor of the steam engine. And 1 watt is defined as 1 joule per second, which makes sense as we're defining this as energy, which is in joules, per time, which is in seconds. The other standard of power that is used is a horsepower. That conversion is 1 horsepower is 746 watts. Just as we use energy in all sorts of everyday applications, we have watts, we have power usage in all of those everyday applications as well. For example, for a light bulb is converting electrical energy into light and thermal energy at 100 joules per second. A light bulb is usually rated at 100 watts or 60 watts. And that's the measurement of the total amount of power that that light bulb is using. For the old style light bulbs, much of that power goes to thermal energy. It goes to heat. And unfortunately, that's wasted energy. The light was just a small fraction of that energy. More recent fluorescent and LED lights create light at the same rate as if they were the old 100-watt bulbs. However, using LEDs brings the thermal energy way down while keeping the amount of light produced, and thus the actual wattage, the actual power used by a new LED light bulb is much less, and that's how they're so efficient and they save energy. We as people also use energy and produce power all the time. We have chemical energy in the food that we eat. That chemical energy is turned into mechanical energy by our bodies, by lifting things, by propelling ourselves, by on a bicycle, propelling ourselves and the bicycle. And we have about 350 watts that we can produce as a peak amount. On the other hand, a gas furnace also produces energy. It turns chemical energy of the gas into thermal energy to heat up water for a hot water heater or to run an air conditioning system. In that sort of situation, you're producing about 20,000 watts. So it can be quite a bit when you're dealing with a much larger system than a human. When a force does work on an object, energy is transferred. And power is this rate of doing work, this rate of energy transfer. We see often when we talk about the rate of doing work, that's another way of saying the time derivative of doing work is the same as the time derivative of the system. since the amount of work done will be an increase in the energy of the system, and both will be positive, or negative work will remove energy from the system, and the derivative of the energy of the system will be negative as well. In either case, this is the power being offered by that force. We've talked about the work done by a force as the force times the displacement times the cosine of the angle between the two as part of the dot product. If we want to take the derivative of the work done in order to find the power, we can say, if we assume the force is constant, which we've done thus far, the angle between the force and the displacement would be constant as well. These two terms would both be constant and would not change when we take the derivative. Thus, the only thing that we would differentiate would be displacement, and if we differentiate displacement, we get velocity. Thus, we can come up with a expression for the derivative of the work done, which is itself the power being produced by the force. The power produced by the force is the magnitude of the force times the velocity of the object that is feeling that force times the cosine of the angle between the two. And that is our relationship that we use for power, using the same idea where we have the force as a constant value. The velocity is the motion along the direction of the displacement with an angle between the force and the velocity. We can treat it as a dot product, or we can use the cosine theta to project the force into the direction of the velocity.